We have seen how the Caesar cipher works and why it can be broken. Now we go deeper into the mathematics that makes it tick. By the end of this lesson, you will be able to describe the cipher with a formula, understand modular arithmetic, and write a working Python implementation. Before we can write a formula for the Caesar cipher, we need to map each letter to a number. By convention, A maps to 0, B to 1, and so on up to Z at 25. This gives us 26 integers, one for every letter. We start from 0 rather than 1 because it makes the modular arithmetic clean, as we will see in a moment. Take the letter H as an example. H is the 8th letter, but in zero-based numbering it sits at index 7. Now for the key mathematical idea, modular arithmetic. Consider encrypting the letter Z with key 3. Z is at index 25. Adding 3 gives 28. But there is no letter at index 28. The alphabet only runs from 0 to 25. We need a way to wrap back around to the beginning. The answer is modular arithmetic. 28 modulo 26 equals 2. The remainder after dividing 28 by 26. Index 2 is C, so Z encrypted with key 3 gives C. Think of it like a clock. After 12 comes 1. The count wraps around. Our alphabet works the same. After index 25 comes 0 again. Modular arithmetic is the mathematics of this cyclic counting. We can now write the Caesar cipher as a formal function. To encrypt letter X with key K, add K to X, and reduce modulo 26. Decryption is the inverse. Subtract K instead of adding it, still modulo 26. Python's percent operator handles negative results automatically, so no extra correction is needed. Let us trace through encrypting the word crypt with key 9, applying the formula to each letter. Watch how some letters shift normally and others wrap around the end of the alphabet. C is at index 2. 2 plus 9 is 11. 11 modulo 26 is just 11. Index 11 is L. R is index 17. 17 plus 9 is 26, exactly the length of the alphabet, so there is no letter at that index. 26 modulo 26 is 0, and index 0 is A. The modulus has wrapped us right back round to the start. Y is at index 24. 24 plus 9 is 33. 33 modulo 26 is 7, and index 7 is H, another wrap. P is index 15. 15 plus 9 equals 24, comfortably inside the alphabet. Index 24 is Y, no wrap needed here. And finally T at index 19. 19 plus 9 is 28. 28 modulo 26 is 2, and index 2 is C. Applying the formula letter by letter, CRYPT becomes LAHYC with key 9. 2 letters shifted cleanly, 3 wrapped around the end of the alphabet, and the modulus handled every case with the same single expression. There is one special value of the key worth examining on its own: 13. When the key is 13, the encryption and decryption formulas become identical. Both just add 13 modulo 26. This special case is called ROT13. The reason is that 13 plus 13 equals 26, and 26 modulo 26 is 0. Applying ROT13 twice leaves you where you started. It is its own inverse. Hello encrypted with ROT13 gives URYYB. Applying ROT13 again to URYYB and you get back hello. This brings us to an important distinction. Encoding is a transformation using a public known scheme. Anyone who knows the scheme can reverse it. There is no secret. The purpose is format conversion or light obfuscation, not security. Encryption requires a secret key. Without that key, reversing the transformation must be computationally infeasible. All security comes from keeping the key secret. ROT13 uses a fixed key of 13 that everyone knows. There is no secret involved. It is encoding. The Caesar cipher with an undisclosed key is encryption, weak as it is. ROT13, by definition, is not. Now let us turn this mathematics into working Python code. Python provides two built-in functions for this. Ord, short for ordinal, converts a character to its integer code point. CHR, short for character, does the reverse. Ordinal of A gives 65, its ASCII code. Subtracting ordinal of A from any uppercase letter gives it 0-based index. The percent operator is Python's modulo. 7 plus 13 is 20. 20 modulo 26 stays 20. Adding the ordinal of A back to that result converts the index to the letter U. Here is the complete ROT13 function. It iterates over each character, converts uppercase letters to 0-based indexes, applies the formula, and converts back. Non-letter characters pass through unchanged. Calling ROT13 on hello gives URYYB. Calling it again on URYYB gives back hello, the self-inverse property in action. Your exercise. Adapt ROT13 to accept any key from 1 to 25. The only change needed is replacing the hard-coded 13 with the key parameter. To decrypt, pass 26 minus the key. Adding the complement modulo 26 reverses the shift. Test with crypt and key 9. The output should be LAHYC. You now have everything needed to implement your own Caesar cipher from scratch. Before we close the Caesar cipher chapter, there is one more weakness worth knowing. English text has highly predictable letter frequencies. E appears in roughly 12.7% of all text. The Caesar cipher does not destroy these frequencies, it just shifts the entire distribution. If E is the most common letter in English, then the most common letter in Caesar encrypted English is the encryption of E. An attacker counts letter frequencies in the ciphertext and identifies the peak. The peak is almost certainly the encryption of E. The key is then just the difference between the ciphertext peak index and E's index, modulo 26. No brute force, no guessing, one calculation. Frequency analysis can break the Caesar cipher in a single step, even faster than brute force. The Caesar cipher fails on two fronts, a key space small enough to brute force by hand, and preserved letter frequencies that make it breakable by analysis alone. The Visionaire cipher was invented specifically to defeat both of these attacks. It uses a repeating keyword that applies a different shift to each letter, scrambling the frequency distribution and expanding the key space dramatically. That is where we are headed next.